In this work example, we're looking at question number 1 from paper 2. And the very first thing it wants us to do is distinguish between vector and scalar quantities. Certainly a foundational idea in physics. You should know as a student of physics that a vector quantity is one with magnitude and direction, and a scalar quantity has magnitude only. And you could put that in your own words. The electric field strength E at a distance x from an isolated point charge Q is given by the equation E equals Q over x squared B, where B is a constant. Use the definition of electric field strength to show that E has SI base units of kilogram meter per amp per second cubed. All right, so the definition of electric field strength is force per unit positive charge. And so I'll substitute in some units now. Newtons of force, coulombs of charge. So one way to think about electric field strength is a Newton per coulomb. Now, somehow these units here have to be those units there. Let's see what we can do. All right, so a Newton is a kilogram meter per second squared. That's just the Newton. And that comes from F equals ma. So a Newton of force is a kilogram meter per second squared, right? Kilogram of mass meter per second squared of acceleration. So there's the Newton. A coulomb, we could think about the equation Q equals IT. So a coulomb of charge is an amp of current times a second of time. And so down here we have an amp second. And I think that gets it, right? And so if I just kind of clean this up, I have a kilogram meter per amp per second cubed. And that's that. So nice. All right, the question goes on to read, use the units for E given in B1. So it's saying use these units here to determine the SI base units of B down there. All right, so I'm going to make this substitution here on the left side. Again, just working with the units. I got kilogram meter per amp per second cubed. I'm going to be careful about the order that I write those variables in, as to not have incidental or accidental profanity on my calculations. Try to avoid it where you can. All right, so on the right side over here, we got a coulomb of charge here, but I'm just going to say it's an amp second, right? Because we already kind of showed that over here. So a coulomb of charge would be an amp second. This is all units here, right? So no quantities. X here, they say is a distance, and so that's going to be meters squared. And so now B has some units that go in this box right here. And maybe I need to extend my box to the numerator also. There could be some units up there. And I've got to make, this side look like this side. And so everything in this box is going to be my answer for B. And so if I look at the left side of the equation, I got a kilogram there, and so I need a kilogram there. I've got to cancel out these meters and still have a meter left over in the numerator. And so what do I need? I need meters cubed up there, kilogram meters cubed. And then I'll cancel out those and give me that. And then I need to have an amp down here. So I've got to cancel out this amp. Still have one left over. So I have amp squared in the denominator. And then I need what? Seconds cubed. And I only have a second in the numerator. So I need seconds to the 4th power down there. All right, so not complicated at all. The SI base units of B are just kilogram meters cubed per square amp per second to the 4th power. Nice. We just got to sort of trust the units, and everything's going to cancel out, to give you what it suggests you should get on the left side there, kilogram meters per amp per second cubed. All right, 6 marks for that. So that's question 1 from this paper 2. What about question 2 from paper 2? Define acceleration. Any student of physics who studied some kinematics will know to define acceleration as the rate of change of velocity. And that's the best way to define it. Acceleration is the rate of change of velocity. You should not just write delta V over delta T, but rather put that into words. The rate of change of velocity, that's acceleration. All right, a steel ball of diameter 0.08 meters is released from rest and falls vertically in air as illustrated in figure 2.1. It says a horizontal beam of light of negligible width is a vertical distance of 0.28 meters below the bottom of the ball when it is released. The ball falls through and breaks the beam of light. explain why the force due to air resistance acting on the ball may be neglected when calculating the time taken for the ball to reach the beam of light. So I think a key word there is a steel ball, right? So it's steel, it's got pretty appreciable density, and it's going to just sort of barrel through the air. The air is not going to have too much effect on it there. It's also over a very short distance, right? So this is only like 20 centimeters. Well, I guess they're saying the diameter of that. So it's, about 30 centimeters that it's falling. So it's not really enough, time in the air or enough, air between where it's falling for the wind or the drag to have an appreciable effect. But steel is sort of the key word there. It's a steel ball. Calculate the time taken for the ball to fall from rest to position P, where the bottom of the ball touches the beam of light. Okay, so we want to calculate the time taken for that. That shouldn't be too bad. So we defined acceleration as the rate of change of velocity. That's final velocity minus initial velocity over time. Could we use this to solve for the time? I don't think so, because while we do know the initial velocity is 0, we don't know what the final velocity is right here. So we have two unknowns and we couldn't solve it. We could remember that the displacement, which is given, is equal to the initial velocity times time, which that's 0, plus 1/2 AT squared, and A is the acceleration due to gravity here. And so this is going to be our way forward. It's nice that the initial velocity is 0, because if this were a non-zero value, then we'd have a quadratic that we need to solve, right? We'd have to solve for T, where it's squared in this term and it's just by itself here. And so thankfully that term goes away and we have a more simpler problem to solve. So we have 0.28 meters of displacement equals 1/2 9.81 meters per second squared times time squared. And then we can just solve for time. So 0.28 divided by 1/2 is the same thing as doubling it, right? And then divide that by 9.81 and then take the square root of that. We get 2.389 or so seconds, 0.2389 seconds. So you probably round that to 0.24. 0.24 seconds for it to reach the bottom of that beam of light. Determine the time interval during which the beam of light is broken by the ball. All right, and so they gave us the diameter of the ball. 0.02 or something, 0.08 rather, so 8 centimeters. So we're trying to calculate now, how long it's going to take for it to move 8 centimeters. All right. The trouble is now we do have non-zero initial velocity. And so what's the simplest way to do this? We could S equals UT plus 1/2 AT squared. So we have the same, sort of equation, the same acceleration, but we have to solve for the velocity right there. And then we just use the displacement or the diameter of the ball itself as the displacement. So that seems tough. We'd have to calculate something else. The other way we could do it is 1/2 U plus VT, but again, we don't know. This one's even worse. We'd have to calculate the initial velocity here and the final velocity first, so that's no good. We could do V squared equals U squared plus 2AS while we're just going through our equations of motion here. And again, we don't know the velocities. So the last one is just the definition of acceleration that I kind of still have up here. And so that's V equals U plus AT. Determine the time interval during which the beam is broken. There's really no straightforward way of doing that. So if we calculated the velocity, right here, right as it's breaking the beam, we could say that the velocity is going to be 0 plus 9.81. And we've already calculated it's going to take 0.2389 seconds or so to reach there. So it's not too bad to get the velocity, which again, we're going to calculate the final velocity here because it was dropped from rest. So it has some sort of speed just before it breaks the beam. We're going to then substitute that value in here for the initial velocity. But then I think we've got the same problem. We're going to have a quadratic to solve if we do it that way. That's no good. So maybe what we'll do is, no, we're going to solve that for time. So we could plug in that initial velocity here to figure out the final velocity, and then, you know, substitute it into like this equation to avoid the quadratic. So it's like, do you want to solve a quadratic equation, or do you want to just use two equations? I leave it to you. So the velocity of the ball right at this moment that it sort of touches the beam is 2.34 meters per second. If I then said 2.34 meters per second squared plus twice 9.81 times 0.08 equals v squared, then I could calculate its sort of final speed a moment later, right? Like when this edge of the ball sort of breaks the photo gate. So let's solve that one real quick. It's going to be 2.34 squared plus 2 times 9. So I get v squared is 7.04. So v is like 2.65. So we would expect it to, you know, it's only undergone a displacement of 8 centimeters. It's picked up a little bit of speed, right? And so these numbers sort of align with that thinking. All right, so now we want to try to figure out the time here, this time interval, using this equation, kind of the simplest one. So I'm going to rewrite it down here. S equals 1/2 u plus v t. 0.08 equals 1/2 2.34 plus 2.65 t. You're sort of averaging the motion here. So it's like from this speed to this speed, how much time does it take if that's the displacement? So 2.65 plus 2.34, about 5 by 2. So 0.08 divided by 2.495. And you get a time of 0.03 seconds, which again, it should be a really small, you know, time interval there. Once you solve this 2.34, like I said, you could have substituted in here for u, and then you would have had a quadratic equation to solve. It's still 9.81 meters per second squared, you know, the acceleration due to gravity. So you know sort of the displacement, the initial velocity, and the acceleration. You just have a, you know, a quadratic equation to solve. So use your quadratic formula, or, you know, use another equation of motion like I've done here. Finally, it says a different ball is released from the same position as the steel ball in B. The ball has the same diameter, but a much lower density. For this ball, the force due to air resistance cannot be neglected as the ball falls. State and explain the change, if any, to the time interval during which the beam of light is broken by the ball. Well, it's going to be moving slower, right? Because the air resistance is going to affect it more dramatically. And so you'd say it would take longer for it to, you know, the time interval during which the beam of light is broken would be, you know, greater because it's moving more slowly, right? So it's going to take more time to sort of travel through. So you kind of put that in your own words. So instead of a steel ball, it's like a beach ball, right? So as it falls, it's going more slowly. It's going to take longer for that to break through. And that's question 2 from paper 2. But you might be wondering about question 3. Question 3, Newton's third law, of course. Newton's third law of motion is about force pairs. Forces exist in pairs. They're equal in magnitude. They're opposite in direction. Some important truths about those force pairs that you should be aware of as a student of physics. Those forces are of the same type. So if we have a gravitational force, then there's a gravitational force pair. If it's a contact force, like a normal force, then there is an equal and opposite, sort of contact force. Just because forces are equal and opposite does not automatically qualify them as a Newton's third law force pair. Those forces always act on two objects. Okay, the Newton's third law force pair is never acting on the same object. You could have a block like this mass down here resting on a surface, and it's got weight acting down and it's got a normal force acting up, and those forces are equal and opposite, and they are not a Newton's third law force pair because the normal force is a contact force and the weight force is a gravitational force. There's a normal force of the table on the block, but there's also an equal and opposite force of the block on the table, another contact force. Okay, and so there we'd be considering sort of like, well, what's the force acting down, on the table, right? Those are the two objects. The other object that's interacting with the block for the weight force is the planet Earth underneath this lab bench, right? That's sort of pulling down on the block, and the block pulls up on the Earth with equal and opposite force. And so those vectors are oftentimes not important because we're only considering, this object. But we can be aware, Newton's laws as acting on two objects, always two objects interacting. Block X, a block X of mass m sub x slides in a straight line along a horizontal frictionless surface as shown in figure 3.1. So I give you speed there. And then it says the block X moving with speed 5v collides head-on with a stationary block Y of mass m sub y. The two blocks stick together and then move with a common speed v as shown. We are to use the conservation of momentum to show that the ratio of the masses is equal to 4. The conservation of momentum says that the initial momentum equals the final momentum. And I'm afraid that's the only clue I'm going to leave you with here, YouTube, and you're on your own to finish the rest. Come back and join us next time for the continuation of question 3 from this paper 2. This is Dr. Schleif, still living the physics life. See you next time.